a fundamental tool with a wide variety of applications in engineering, physics, biology, economics, and more than the world has ever understood or is yet to find out, is what we know as derivatives.
Hi! For today's video, we'll discuss about the two main branches of calculus, which is the derivatives or differential calculus and integrals or integral calculus. A derivative is a function that reveals the slope of a line tangent to a curve at any point and provides the instantaneous rate of change. Let us say we have a random curve. And if we can recall the definition of tangent line, we know that every point on this given graph has a different tangent line. The derivative is supposed to give us the slope of each of these tangent lines, but without having more than one certain point, how would we find the slope? Unlike the graph of a linear function, where we can freely choose any 2 points to use on a slope formula, our curved graph has a slope that changes everywhere. Therefore, the tangent line also changes. To answer how we would find the slope of a tangent line at any point, which we will now refer to as point 1 or P1. We will use this graph with a curve and choose a second point that we will call P2. Then we'll draw a straight line through. Let us label the horizontal distance of the first point from the second point as change in x or delta x. Then the second point will have an x-coordinate of delta x more than x or x plus delta x. Having the x and y pair of the first point with the x-coordinate as x and the y-coordinate as f of x, and the x and y pair of the second point with the x-coordinate as x plus delta x and the y-coordinate as f of x, delta x, we can now use the slope formula, which leaves us the slope of the secant line or the difference quotient, which is only an approximation of the slope. How we will turn this into the slope of a tangent line or the exact slope? We will pick a point from the right side of the curve that moves closer and closer to the left side and will cause the horizontal distance get smaller and give a more accurate estimation of a slope. By taking the limit of the rate of change in x as it approaches to 0, we will obtain the perfect calculation of the slope. The slope of the secant line now becomes the slope of the tangent line and defines the derivative. This topic can be applied to various fields. A few common examples include business, to estimate profit and loss, physics, that concerns derivatives with respect to time, including velocity, acceleration, momentum, and derivatives with respect to position, the potential, and kinetic energy. And of course, mathematics, regarding the study of functions. Let us use a simple scenario. Suppose you are riding on your bike with your friends. Then, you encounter 2 steep roads that lead to the same route. One challenges you to a race. At first, you thought it was not as hard as it looks, considering that both hills have the same distance to reach the finish line. And your opponent seemed tired, so you expected to have the upper hand. But surprisingly, you lost. After the race, you decided to climb both hills. Then you notice that one seems steeper than the other one. When you express your concern with your friends, they didn't believe you. So you use what you learned from a lesson in calculus about derivatives and prove that the slope you climbed was higher and more challenging than your opponents. A symbolic system for representing mathematical objects and concepts is known as notation. Notation is constructed in such a way that certain symbols represent specific things and communication is efficient. So what is a derivative notation? Derivatives are the result of a differentiation procedure applied to a function or expression. The way we express derivatives theoretically is through derivative notation. Similarly, the derivative of a function, which is a function that represents the slope of the tangent line to the original, has several notations. The first one is Lagrange or Lagrange's notation. This was introduced by the Italian-French mathematician Joseph Louis Lagrange. In Lagrange's notation, the derivative of f is expressed as f apostrophe, pronounced as f prime. When dealing with function with only one variable, this notation is perhaps the most popular. Instead of a function, for example, we have an equation of y is equal to f of x, we can write it as y prime to represent the derivative. The second one is the Leibniz notation. This notation was introduced by the German polymath Gottfried Wilhelm Leibniz. In Leibniz notation, the derivative of f is expressed as d over dx of f of x. For example, we have an equation of y is equal to f of x. We can write it as dy over dx. The d over dx is an operator that shows a differentiation with respect to x. Example, x squared can be written as d over dx of x squared. The third one is the Newton's notation. This notation was introduced by an English mathematician, Isaac Newton. In Newton's notation, also known as the dot notation, the derivative of f is expressed as f dot, and the derivative of y is equal to f of x is expressed as y dot. This notation is mostly common in physics and other sciences where calculus is applied in real-world context. The last one is the Euler's notation. This notation was introduced by a Swiss mathematician, Leonhard Euler. In Euler's notation, we denote a derivative with a capital E, that is d f of x or dy. This notation has its own limitation, though as it doesn't tell us what variable to differentiate with respect to, and is only used when understood clearly.
The increment method is a long method that is used to find the derivative of a function. In calculus, if there is a change in a variable, it is called increment and is denoted by the Greek letter delta. So if y is equal to f of x and there is a corresponding change in y, then there will also be a change in f of x. So let us derive a formula for the increment method by following these 4 steps. Let us apply these steps for y is equal to f of x. By the first step, we will replace y by y plus delta y and x by x plus delta x. So we will get y plus delta y is equal to f of x plus delta x. Next, we will subtract y from y plus delta y and the value of y in the other side of the equation. So we will come up with delta y is equal to f of x plus delta x minus y. We basically transpose y to the other side of the equation. Next, since y is equal to f of x, we can say that delta y is equal to f of x plus delta x minus f of x. For the third step, we will divide both sides of the equation by delta x. So we will come up with delta y over delta x is equal to f of x plus delta x minus f of x over delta x. We will then get the limit of the function as delta x approaches 0. So we will have the limit of delta y over delta x is equal to f of x plus delta x minus f of x over delta x as delta x approaches 0. Since the limit of delta y over delta x is equal to dy over dx, we can say that dy over dx is equal to the limit of f of x plus delta x minus f of x over delta x as delta x approaches 0. So for a formal definition, the derivative of the function f is that function denoted by f prime such that its value at a number x in the domain of f is f prime of x is equal to the limit of f of x plus delta x minus f of x over delta x as delta x approaches 0, if this limit exists. Here, we just replace dy over dx with f prime of x since both are for getting the derivatives. And if x sub 1 is a particular number in the domain of f, then f prime of x sub 1 is equal to the limit of f of x sub 1 plus delta x minus f of x sub 1 over delta x as delta x approaches 0, if this limit exists. The difference of these two equations are simple. The first equation is used if there is no specific value of x, while the second equation is used if there is a value of x. Here we have a 4-step rule that we will follow in order to get the derivative of a function using the increment method. Find the derivative of f of x equals 2x minus 5. We will first substitute all the values of x in the given function by x plus delta x, so we will obtain the limit of 2 quantity x plus delta x minus 5 minus f of x over delta x as delta x approaches 0. We will then subtract the function from the given values. That basically means that we will substitute the value of f of x. So we will come up with the limit of 2 quantity x plus delta x minus 5 minus quantity 2x minus 5 over delta x as delta x approaches 0. After that, we can simplify the equation. We will simply distribute 2 to x plus delta x and the negative sign or negative 1 to 2x minus 5. We will then obtain the limit of 2x plus 2 delta x minus 5 minus 2x plus 5 over delta x as delta x approaches 0. Here we can cancel 2x and negative 2x. We can also cancel negative 5 and 5. So we will obtain the limit of 2 delta x over delta x as delta x approaches 0. We will then divide the result by delta x. Over here, we can cancel delta x, so we will come up with the limit of 2 as delta x approaches 0. Lastly, we will get the limit as delta x approaches 0. And by the limit theorem 2 or the limit of a constant, the limit of 2 is equal to 2 as delta x approaches 0. So we will obtain a final answer of f prime of x is equal to 2.
So here is an example of solving derivatives using increment method. Find the derivative of f of x equal to quantity 4x plus 8 over quantity 5x plus 12. Keep in mind that when using the increment method to solve the derivative of a function, we must follow the 4-step rule and we will use the formula f prime of x is equal to the limit of quantity f of x plus delta x minus f of x all over delta x as delta x approaches to 0. First, replace the values of x's with x plus delta x in the given equation. So, f prime of x is equal to 4 times the quantity of x plus delta x plus 8 all over 5 times the quantity of x plus delta x plus 12. For the second rule, we must subtract f of x to the equation we formed. F prime of x is equal to quantity 4 times the quantity of x plus delta x plus 8 all over 5 times the quantity of x plus delta x plus 12 minus 4x plus 8 over quantity 5x plus 12. Then just simplify. Distribute the 4 and 5 to the x plus delta x. F prime of x is equal to quantity 4x plus 4 delta x plus 8 all over quantity 5x plus 5 delta x plus 12 minus quantity 4x plus 8 over quantity 5x plus 12. Get the LCD and then simplify. Now we got f prime of x is equal to 20x squared plus 20x delta x plus 40x plus 48x plus 48 delta x plus 96 minus quantity 20x squared plus 20x delta x plus 40x plus 48x plus 40 delta x plus 96 all over the quantity of 25x squared plus 25x delta x plus 120x plus 60 delta x plus 144. Following that, we just simply cancel out the same terms. This will result the numerator being 48 delta x minus 40 delta x. Simplify, and now we got 8 delta x all over the quantity of 25x squared plus 25x delta x plus 120x plus 60 delta x plus 144. For the second to the last rule in increment method, we must divide the form equation by delta x. So 8 delta x all over the quantity of 25x squared plus 25x delta x plus 120x plus 60 delta x plus 144 divided by delta x. Simplify. 8 all over the quantity of 25x squared plus 25x delta x plus 120x plus 60 delta x plus 144. The last step is to get the limit of the equation as delta x approaches to 0. The limit of equation 8 over the quantity of 25x squared plus 25x delta x plus 120x plus 60 delta x plus 144 as delta x approaches to 0 is 8 all over the quantity of 25x squared plus 25x times 0 cancelled out plus 120x plus 60 times 0 cancelled out again plus 144. So for our final answer, the derivative of the equation f of x equal to quantity 4x plus 8 over quantity 5x plus 12 is f prime of x equal to 8 all over the quantity of 25x squared plus 120x plus 144. But wait, did you know that we can solve this equation a lot faster compared to the increment method? We can save a lot more time than the increment method with the help of theorems in differentiation. So now we will find the derivative of the equation f of x equal to quantity 4x plus 8 over quantity 5x plus 12. But the theorems in differentiation approach. We will apply the quotient rule and use the formula f prime of x is equal to quantity of g of x times h prime of x minus the quantity of h of x times g prime of x all over g of x squared. But first, let g of x equal to 4x plus 8 and h of x equal to 5x plus 12. Then find the derivative of the two. G prime of x is equal to 4 times 1 plus 0. We applied the sum rule, and then the derivative of 4x is 4 since we all know that according to the identity rule, the derivative of x is 1. And the 8 becomes 0 because of the constant rule. So g prime of x is 4. H prime of x is equal to 5 times 1 plus 0. We applied the sum rule, and just like what I said earlier, according to the identity rule, the derivative of 5x is 5 since the derivative of x is 1. And the 12 becomes 0 due to the constant rule. So h prime of x is 5. After that, we will just substitute the values we got and then simplify. F prime of x is equal to quantity 5x plus 12 times 4 minus quantity 4x plus 8 times 5 all over the quantity of 5x plus 12 squared. By further simplifying, f prime of x is equal to quantity 20x plus 48 minus quantity 20x plus 40 all over the quantity of 25x squared plus 120x plus 144. Cancel out and then subtract 48 and 40. And tada! Here's our final answer. F prime of x is equal to 8 all over the quantity of 25x squared plus 120x plus 144. As you can see, using differentiation theorems is much faster than using the increment method. And still, the derivative obtained by both methods is the same.
The theorems on differentiation are the rules that allow us to find the derivatives of a function easier than when we use the definition of a derivative, which makes even the simplest of functions longer to solve. There are 7 given differentiation rules. The first one is the constant rule of differentiation. In this theorem, it is stated that if f of x is equal to a constant for all x, then f prime of x is equal to 0. To prove this, let us use the limit definition of the derivative as a function of x. If we use a as our constant, then if f of x is equal to a for all x, f prime of x is the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0. A minus a is equal to 0, we will then have the limit of 0 over delta x as delta x approaches 0. By simplifying this, we will have f of x is equal to 0, and since the derivative of any constant is equal to 0, then this process proves the constant rule of differentiation. The second theorem is the power rule of differentiation that is written in the form f of x is equal to x raised to n, where n is a constant and a natural number, then its derivative will be f prime of x equals n times x raised to n minus 1. We need to show that the first derivative is n times x raised to n minus 1 by using the definition of a derivative in the form the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0. Since f of x is equal to x raised to n, then we will have quantity x plus delta x raised to n minus x raised to n all over delta x. To show that the current given limit is equal to n times x raised to n minus 1, we will use the binomial theorem. Now, we will let n be in the set of natural numbers, and by doing that, we will be left with this form of the binomial theorem, which we can simplify to end up with n times x raised to n minus 1. This proves the limited form of the power rule of differentiation.
For the third theorem, the constant multiple rule of differentiation. This rule states that the derivative of a constant times a function is equal to the constant times the derivative of a function. By using the definition of the derivative in the given form, the limit of a times f of x plus delta x minus a times f of x all over delta x as delta x approaches to 0. Now, we will factor out our constant from the interfraction, and we will observe that since delta x approaches 0, the limit approaches the derivative of f at x. And now, we are left with our constant a times f prime of x, and this proves the constant multiple theorem. The fourth theorem is the identity rule of differentiation. This means that the derivative of a function is equal to 1, so if we have a function with x as an input, we should also have it as its output. To prove this, we will be using the definition of derivative, where f prime of x is equal to the limit of f of x plus delta x minus f of x all over delta x as delta x approaches to 0. Again, the input of a function is the same as the output. Therefore, the f of x plus delta x will become x plus delta x, and negative f of x will become negative x. By simplifying this, x minus x is cancelled out, and we are left with delta x divided by delta x, which is equal to the limit of 1 as delta x approaches 0. Since delta x became 1, we can now remove the limit, and so our final answer is 1. And this proves that the derivative that f of x is 1.
The fifth rule of differentiation is the sum and difference rule. The first one is the sum rule of differentiation. For the sum rule, the derivative of the sum of the two functions is equal to the sum of their individual derivatives. We can prove this by using the limit definition for derivatives. First, let's have a new function called the f of x, which is equal to the sum of the given individual functions. Second, by applying the limit definition for derivatives, we will get f prime of x equals to the limit of f of x plus delta x minus f of x all over delta x as delta x approaches to 0. Third, we will simply replace x with x plus delta x to obtain the following limit. For the fourth step, the negative sign on the limit above will be applied on both terms, and so negative f of x plus g of x will become negative f of x and negative g of x. Lastly, as you can observe, the limit can be split up into two. So we have the limit of f of x plus delta x minus f of x all over delta x as delta x approaches to 0 plus g of x plus delta x minus g of x all over delta x as delta x approaches to 0. Simplify the limit of f and g, f prime of x plus g prime of x, and that's the sum of the derivative. The process of proving the sum rule is similar to the process used in proving the difference rule. They only differ on the sign used. Let f of x equals to f of x minus g of x. Therefore, f prime of x is equals to limit of f of x plus delta x minus f of x all over delta x as delta x approaches to 0. The limit of f of x minus g of x plus delta x minus f of x minus g of x all over delta x as delta x approaches to 0 can be written as f of x plus delta x minus f of x plus g of x plus delta x plus g of x all over delta x as delta x approaches to 0. It can be written as limit of f of x plus delta x minus f of x all over delta x minus g of x plus delta x plus g of x all over delta x as delta x approaches to 0. We can simplify it and we can get f of x minus g of x is equals to f prime of x minus g prime of x, and that's the difference of the derivatives. The product rule is the sixth theorem of differentiation that says the derivative with respect to x of the product of two functions f of x times g of x is equal to f of x times g prime of x plus prime of x times g of x. To prove this, let's use f of x equals to the product of f of x times g of x. If we use the definition of a derivative, we can form f prime of x is equal to the limit of f of x plus delta x minus f of x all over delta x as delta x approaches to 0. We can replace the f of x function to get the limit of f of x plus delta x times g of x plus delta x minus f of x times g of x all over delta x as delta x approaches to 0. For the next step, we're going to subtract and add the term f of x plus delta x times g of x to the numerator, which will give us the following limit. We will split this up into two separate limits. In the first limit, we're going to factor out f of x plus delta x, and for the second limit, we're going to factor out g of x. Observe that in the first limit where h approaches 0 of f of x plus delta x, if we substitute in delta x equals 0, we'll be left with f of x times limit of g of x plus delta x minus g of x all over delta x as delta x approaches to 0. And for the second limit where delta x approaches to 0 of g of x, we will repeat the steps done in the first limit to end up with the following. If we simplify this, we will get f of x and the definition of g prime of x plus g of x and the definition of f prime of x, which completes the proof of the product rule of differentiation.
The seventh and last theorem of differentiation is the quotient rule. To prove this theorem, we find the derivative of the quotient between f of x and g of x by using the definition of the derivative. Instead of dividing this limit by delta x, we multiply this by 1 over delta x to avoid getting stacked fractions. After this, we will follow a step similar to how we proved the product rule. Let's replace f of x plus delta x by the value of the function at x plus the appropriate change in the function. And g of x plus delta x will become the value of g at x plus the appropriate change in the function g. In the next step, we will be cross-multiplying to combine the separate fractions. By expanding, we will obtain the following. If we observe the numerator, we can cancel f of x times g of x minus f of x times g of x, then we will be left with a change of f and g in the numerator and the change of x in the denominator, which we can pair with delta x and factor out. This leads us to the limit of the first term, g of x times delta f over delta x minus the second term, f of x times delta g all over delta x. We'll also include the two terms left in the denominator and factor them out as 1 over g of x plus delta g times g of x. By doing this, delta x can approach 0 where delta f over delta x approaches the derivative of f at x, delta g over delta x will be approaching the derivative of g at x, and since delta g approaches 0, we will have g of x times g of x, therefore we have g of x squared. If we simplify the limit we're left with, we will obtain f prime of x times g of x minus f of x times g prime of x all over g of x squared. This proves the quotient rule of differentiation, wherein the derivative of f over g is the derivative of f times g minus f times the derivative of g over g squared.
One application of derivatives in real life is determining the speed or distance covered. Let's try solving one problem including this application. So here's a sample problem providing an application of derivatives in real life. In 60 minutes, a car traveled f of x is equal to 8x plus 15 kilometers. Calculate the distance it traveled. We can solve it using the increment method by using formula 3. F prime of x is equal to the limit of f of x plus delta x minus f of x all over delta x as delta x approaches to 0. Let's now substitute x plus delta x in the x of the equation 8x plus 15 and just write 8x plus 15 in f of x. We will have limit of 8 times the quantity x plus delta x plus 15 minus the quantity 8x plus 15 all over delta x as delta x approaches to 0. Next, distribute 8 in the quantity x plus delta x and distribute the negative sign in the quantity 8x plus 15. We will have limit of 8x plus 8 delta x plus 15 minus 8x minus 15 all over delta x as delta x approaches to 0. Then, evaluate the numerator. We will have limit of 8 delta x over delta x as delta x approaches to 0. Cancel out delta x. We will have limit of 8 as delta x approaches to 0. By limit theorem 2, we will have the answer f prime of x is equal to 8. Therefore, the distance that the car traveled in 60 minutes was 8 kilometers.
Hi! Welcome to this part of the video which is all about applying derivatives in real life, and I hope you enjoy it. Nevertheless, let's have a recon first on what derivatives are. In mathematics, derivatives are defined as a method to show the rate of change, that is, the amount by which a function is changing at one point. The process of finding the derivative of a function is called differentiation. Nowadays, various applications of derivatives are not only applied in mathematics, it also extends everywhere in real-life settings. For instance, derivatives are applicable in measuring the rate of increase in profit in business. We can also check and calculate temperature variation and which days or months are the hottest and coldest, estimate the likely occurrence of tectonic activities, and to determine the speed and distance covered, as well as velocity and acceleration of an object. Now, let's head out with our examples. Computation of velocity and acceleration of an object is the most applicable plot because the derivative of the position or the position function with abbreviation of s of t will give you a new function that describes velocity, where velocity can be positive or negative in sign, and if you have the derivative of an equation that describes the velocity, you will get the acceleration, the second derivative of the position function. For example, number 1. The displacement in meters of a moving green 1969 mini car in a straight line is given by the equation of motion. S is equals to 6t cubed plus 2t plus 5, where t is measured in seconds. We have to find out A. Find the velocity of the vehicle after 3 seconds, and B. Find the acceleration of the vehicle after 3 seconds. Remember that to find the velocity, we must find the derivative of the position function, then substitute the value of time. So, the derivative of the position function is the same as the velocity equation. We have a polynomial, and to do this, we will apply the sum and difference theorem of differentiation, constant rule, and the use of power rule in each term, where the power of x gets subtracted by 1. Afterwards, the entire function is multiplied by the value of the original power. A. Find the velocity of the vehicle after 3 seconds. So, we have s prime equals 3 times 60 raised to 3 minus 1. For the next term, the exponent of 1 multiplies to 2t raised to 1 minus 1. For the last term, since we have a constant, the derivative of a constant is always 0. Then, simplify. We have 18t squared plus the second term 2t raised to 0. In this part, t raised to 0 is equals to 1 only. We have 2 multiplied to 1 and plus 0. We will have an answer of 18t squared plus 2. To find the velocity of the car, we just need to substitute the value of time. We have s prime is equals to 18t squared plus 2. Then, it will become 18 times 3 squared plus 2. It will come up with 18 times 9 plus 2 with 162 plus 2 with the final answer of 164 meter per second. Therefore, 164 meter per second is the velocity of the vehicle after 3 seconds. Secondly, we need to find the acceleration function. To find the function, we need to solve the derivative of the velocity function or the derivative of the position function with the same process. We have 18t squared plus 2. Apply power rule, constant rule, and sum and difference rule. We'll come up with 2 times 18t raised to 2 minus 1 plus 0. Then, 36t raised to 1 plus 0. Further simplify, we have 36t only. To find the acceleration of the car, we need to substitute the value of time. We have 36t, then substitute 3 with t. We'll have 36 times 3, and we'll come up with 108 meter per second squared. Therefore, 108 meter per second squared is the acceleration of the vehicle after 3 seconds. For our next example, number 2, a balloon is being inflated at a rate of 8 cubic centimeters per second. How fast is the radius increasing when it is 5 centimeters? In this case, there is a rate of change. If you are inflating a spherical balloon, the volume expands with respect to radius. Let's start our computation with the given values of the change in volume with respect to time is represented as dV over dt, equal to 8 cubic centimeters per second. Our radius of 5 centimeters and a volume of 4 over 3 pi r cubed, a constant formula for spheres since we have a spherical balloon. Since we have to find the rate of change in radius as it increases, we have a rate of change in radius with respect to time, dr over dt. To get the values of dr over dt, we have to get the derivative of the spherical formula. We have dv over dt, and 4 over 3 and pi r cubed are constant. We will only get the derivative of radius. Then we will now have dv over dt is equals to 4 over 3 pi, apply power rule. 3 multiplied to r, then raised to 3 minus 1 equals 2. Then multiply it with dr over dt. Then, we will now substitute our values. dv over dt is 8. We can apply division. 3 divided by 3 is 1. We will only have 4 pi only. We have a radius of 5, becoming 5 squared, times dr over dt. Further perform the operations. 8 is equal to 4 pi times 5 squared is 25 times dr over dt. Then have 8 is equal to 4 times 25 is 100. We have 100 pi times dr over dt. To remove 100 pi and get the value of dr over dt, let us multiply both sides with 1 over 100 pi. It will now become 8 over 100 pi. Therefore, the rate of change in spherical balloon as it inflates with radius of 5 centimeters is 8 over 100 pi centimeters per square.
From our previous video, we already know what is derivatives. And we learned how to find derivatives of any function. And now, I'll discuss about integral calculus. Let us say we have a curve that represents y is equal to f of x. And somehow, we will wonder how we will find the area under this curve or above the x-axis. Supposing A and B as our points, So with integral calculus, we can get the approximation value or area between A and B or under this curve. Integral is the opposite of derivatives. It is the area under the curve. It serves as a tool for calculating the area of an arbitrary shape, the length of a curve, and the volume of a solid, typically in mathematics and physics. Integral calculus is a branch of calculus concerned with the theory and applications of integrals. As I mentioned a while ago, integral calculus deals with the total size or value, such as length, area, and volumes. And now, let's proceed with the difference of differentiation and anti-differentiation. Differentiation is the essence of calculus. Differentiation is a method of finding the derivative of a function. A derivative is defined as the instantaneous rate of change in a function based on one of its variables. It is similar to finding the slope of a tangent to the function at a point. If x is a variable and y is another variable, then the rate of change of x with respect to y is given by dy over dx. This is the general expression of the derivative of a function and is represented as f prime of x, where y is equal to f of x is any function if the function f of x undergoes an infinitesimal change of delta x near to any point x. Then the derivative of the function is defined as the limit of f of x plus delta x minus f of x all over delta x as delta x approaches to 0. The antiderivative, also referred to as an integral, can be thought of as the inverse operation for the derivative. In other words, it is the opposite of a derivative. An antiderivative is a function that reverses what the derivative does. One function has many antiderivatives, but they all take the form of a function plus an arbitrary constant. Antiderivatives are a key part of indefinite integrals. Antidifferentiation is an essential tool for evaluating integrals. In fact, you might say that antidifferentiation is pretty much the same thing as finding an indefinite integral. When we antidifferentiate a function, we are simply finding another function whose derivative is equal to the one we started with. So just as differentiation is the process of finding a derivative, antidifferentiation is the catch-all term for any formula, technique, or method of finding an antiderivative. If f is a function, then we can say that f is an antiderivative for f if f prime of x is equal to f of x. If a function has one antiderivative, then it has infinitely many antiderivatives. This is because the derivative of any constant is 0. So if f of x is antiderivative of f of x, and c is any constant, then f of x plus the constant of integration prime is equal to f prime of x plus constant integration prime is equal to f of x plus 0 is equal to f of x. Therefore, f of x plus c is also an antiderivative for f. We call c the constant of integration.
Integrals. In calculus, an integral is a mathematical object that can be interpreted as an area of a generalization of area. Integrals together with derivatives are the fundamental objects of calculus. Other words for integral include antiderivative and primitive. The process of computing an integral is called integration. A more archaic term for integration is quadratic. And the appropriate computation of an integral is termed numerical integration. Integral notation. The S-shaped symbol is called an integral sign. The function f of x is called the integral. The dx part means that x is the variable of integration. The integral is taken from the number at the bottom of the integral sign to the number at the top of the integral sign. The number at the bottom of the integral sign is called the lower limit of integration, while the number at the top of the integral sign is called the upper limit of integration. The integral operator is represented by the integral symbol and has four parts: the expression being integrated, the differential, a start value and an end value. Typically, the operator appears in an expression like this. In plain language, this means that take the integral of the function f of x with respect to dx along range from a to b. Importantly, the differential dx expresses which variable is being integrated. An integral can be interpreted as the area under the curve of a function between the points a and b. The concept is used throughout physics and higher level mathematics. The integral sign is used to represent the integral operator in calculus. The integral operator is an integral that can be geometrically interpreted as the area under the curve of a function between the points a and b. Integrals are a core operator in calculus and are used throughout physics and higher level mathematics. The lower and upper limit. The number a that is at the bottom of the integral sign is called the lower limit of the integral, and the number b at the top of the integral sign is called the upper limit of the integral. Also, despite the fact that a and b were given as an interval, the lower limit does not necessarily need to be smaller than the upper limit. Collectively, we'll often call a and b as the interval of integration. Differential. It relates to the problems of finding the rate of change of a function with respect to the other variables. Moreover, to get the ideal solution, we use derivatives to find the maxima and minima values of a function. In addition, it arises from the study of the limit of a quotient. Furthermore, it deals with the variables such as x and y, functions f of x, and the consequent changes in the variables x and y. Besides, the symbols dx and dy are known as differentials. Moreover, the process of finding derivatives is what we call differentiation. Also, the derivatives of the function are represented by dy over dx. This means that the function is the derivative of y with respect to the variable x. The letter c constant. Given a function f of x, an antiderivative of f of x is any function f of x such that f prime of x is equal to f of x. If f of x is any antiderivative of f of x, then the most general antiderivative of f of x is called an indefinite integral and denoted the integral of f of x with respect to dx is equal to f of x plus c, where c is any arbitrary constant. In this definition, the S-shaped symbol is called the integral symbol, f of x is called the integrand, x is called the integration variable, and the c is called the constant of integration. The process of finding the indefinite integral is called integration or integrating f of x. If we need to be specific about the integration variable, we will say that we are integrating f of x with respect to x. If f of x is an antiderivative of a function f of x, that is, f prime of x is equal to f of x, then g of x is equal to f of x plus c, where c is any constant. Is also an antiderivative of f of x since g prime of x is equal to the prime of f of x plus c equals to f of x and equals to f prime of x. Hence, there are a family of functions only differ by a constant that are antiderivatives of f of x. In order to include all antiderivatives of x, the constant of integration c is used for indefinite integrals.
For this portion, we will be tackling about the basic theorems in antidifferentiation. Over here, we have the indefinite integral, or the notation that we use to denote the antiderivatives of a function. Let's begin with the theorems. For theorem 1, we have the integral of dx equals x plus c. Basically, what we're saying is that dx is equal to x plus c. For example, if our variable of integration is y, then the integral of dy is equal to y plus c. And if it is r, then the integral of dr is equal to r plus c. Next, we have theorem 2 for the constant rule. We have the integral of a times f of x dx equals a times the integral of f of x dx, where a is a constant. Basically, we're just moving the constant out of the integration in this theorem. For a better understanding, let's move on to the examples. Let us evaluate the integral of 6 dx. Applying theorem 2, we will move the constant, which is 6, outside of the integration. So we will come up with 6 times the integral of dx. Since the integral of dx is equal to x plus c through theorem 1, we will obtain 6 times the quantity of x plus c. We can substitute 6 to the quantity of x plus c and come up with the final answer of 6x plus c. We can see that the arbitrary constant remains the same even though we substitute 6 to it. This happened because 6 times c is still equal to a constant. For the next example, we have the integral of negative 1/2 dw. Again, by limit theorem 2, we will move negative 1/2 out of the integration, so we will obtain negative 1/2 times the integral of dw. Through limit theorem 1, dw is equal to w plus c, so we will obtain negative 1/2 times the quantity of w plus c. Simplifying, we will get negative 1/2 w plus c as our final answer. For theorem 3, or the power rule, we have the integral of x raised to n dx equals x raised to n
The integration of a function with no bounds is known as an indefinite integral. Integration is the antiderivative of a function since it reverses the differentiation process. The indefinite integral is a fundamental concept in calculus, and applying limiting points to it converts it to definite integral. Integration is a term used to describe the process of determining the area contained by a curve with respect to one of the coordinate axes. Let's talk about the basic form of integration. The indefinite integral of f of x with respect to x. We have f of x dx is equal to the antiderivative of f of x plus the arbitrary constant c. The first basic integration rule is the power rule of integration. If you are getting the integral of x raised to n dx, it is just equal to x raised to n plus 1 all over n plus 1 plus the constant c. For example, we have the integral of x raised to 7 dx. So first we will get the x raised to n plus 1 and the denominator n plus 1 and then the constant c, which is equal to x raised to 7 plus 1 all over 7 plus 1 plus the constant c. We will get the result of x raised to 8 all over 8 plus the constant c. The next rule of integration is the constant multiple rule for integration. The integration of a multiplied to f of x dx is just equal to a times the integral of f of x dx. In this case, we just put the constant a outside the integration. For example, we have the integral of 5x raised to 4 dx. First, we will put the constant outside the integration. So it will become 5 times the integration of x raised to 4 dx. In this case, we can use the power rule of integration. It will become 5 times the x raised to 4 plus 1 all over 4 plus 1 plus the arbitrary c. We will get 5 times x raised to 5 all over 5 plus the arbitrary c. If we simplify it, we can get x raised to 5 plus the arbitrary c. The next rule is the sum and difference rule for integration. So here, we are given two functions, which is the f of x and the g of x. From the name itself, we will get the sum or difference of the integral, which the integral of f of x plus or minus g of x dx is just equal to the integral of f of x dx plus or minus the integral of g of x dx. For example, we have the integral of 2x plus 4 dx. First, we will separate them, which will be equal to the integral of 2x dx plus the integral of 4 dx. Second, we can apply the constant multiple rule, so it will become 2 times the integral of x dx plus 4 times the integral of x raised to 0 dx. Now we can perform the power rule. It will become 2 times x raised to 2 all over 2 plus 4 times x plus the arbitrary c. And we will get the result of x squared plus 4x plus the arbitrary c. A formal computation of area beneath a function using microscopic slivers or stripes of the region is known as a definite integral. Integrals can be used to indicate the area of the region, which is accumulated value of a function changing over time, or the quantity of an item given its density. They were first examined by Isaac Newton and Gottfried Leibniz, two of the 17th century mathematicians who developed their own systems of integration. The area under a curve between two fixed bounds is called a definite integral. The definite integral has an upper limit equal to b and a lower limit equal to a. In evaluating the definite integral, we have a form of integral of f of x dx from a to b is equal to f of b minus f of a. In evaluating the definite integral, it is similar to the indefinite integral. Example, we have the integral of x dx from 4 to 8. First, we will apply the power rule. So it will become x raised to 1 plus 1 whole over 1 plus 1. Therefore, we can write it as x squared whole over 2. Since we are in definite integral, we will not write the arbitrary c. In this case, we will evaluate it from our lower limit 4 until the upper limit 8. From the formula above, we can evaluate it by f of b minus f of a. It will become 8 squared over 2 minus 4 squared over 2. Then, we can simplify it into 64 over 2 minus 16 over 2. We can simplify it into 32 minus 8, which is equal to 24. Therefore, the integral of x dx from 4 to 8 is equals to 24. The major distinction between indefinite and definite integrals is that indefinite integrals have no bounds, whereas definite integrals have an upper and lower limit.
In this part of the video, we will provide you some techniques that are successfully used in seeking the antiderivatives or integrals of functions, which these integration techniques are computationally useful for proofs. Number 1. U substitution. Substitution rule is like the chain rule in reverse, as we symbolize some base of a function with a single variable like u, allowing us to integrate more simply. Take note that while the chain rule will always work, however, the substitution rule does not lie down the job all the time. We must look for an integral on whether the substitution rule can be applied or not. If we have an integral in the form of f of g of x times g prime of x dx, g of x can be represented as u, while the g prime of x dx turns into du. Then we end up with f of u du, which we can integrate. Number 2. Powers of sine and cosine. In this section, we will get to know how to solve or evaluate such an integral of sine raised to n x, cosine raised to n x dx, where power of sine x and cosine x are greater than 1. In solving this integral, we apply some identities that came from sine squared theta plus cosine squared theta is equals to 1. We have two conditions. First condition is, if n is an odd number, split on a factor of cosine x and use the identity cosine squared x equals to 1 minus sine squared x. On the second case, if n is odd, split on a factor of sine x, apply the identity sine squared x equals 1 minus cosine squared x. Number 3. Trigonometric substitution. This technique works in one of the three specific terms present in the integral. These are square root of a squared minus x squared, square root of a squared plus x squared, or square root of x squared minus a squared. A can be any positive number. We cannot apply substitution rule as there's no term to act as du. However, we can change x into something else that results in getting rid of the radical. With square root of a squared minus x squared, let x be sine theta. If we substitute it with x, the exponent distributes. We get a squared minus a squared sine squared theta. Then factor out a squared to get into a squared quantity 1 minus sine squared theta. In Pythagorean identities, 1 minus sine squared theta is equal to cosine squared theta. Let's make the change, then we are left with a perfect square. Take the square root. We'll come up with a times absolute value of cosine theta. If we take the interval of theta, cosine theta will be positive. Lose the absolute value and left with a cosine theta. At our second expression, let's make x equal to a tangent theta. Then square it, factor out the a squared, apply the Pythagorean identity, get rid of the radical to get a second theta. Then we have square root of x squared minus a squared. We can change x into secant theta. Then perform the process we have used earlier. We'll have a tangent theta. Number 4. Integration by parts. The product rule for differentiation corresponds to technique in integration, which is integration by parts. The product rule says that the derivative of two functions is equal to the first times the derivative of the second times the derivative of the first times second. So the integral of this derivative must be the product of the two functions earlier. Integral of the sum is equal to the sum of the integrals. Then bring the second integral on the other side by subtraction. We'll come up with the formula of integration by parts. In many cases, we have an integral form of f of g of x times g prime of x dx, but this form is easier. This technique for turning one integral into another is called integration by parts and is usually written in more compact form. If we let u equals f of x and v equals g of x, then du equals f prime of x dx and dv equals g prime of x dx, we'll come up with the integral of u dv equals uv minus the integral of v du. Number 5. Rational functions. A rational function is a fraction with polynomials in the numerator and denominator. There is a general method tagged as partial fractions that allows us to integrate any rational function. If the denominator has the form quantity ax plus b raised to n, the substitution u equals ax plus b will always work. The denominator becomes u raised to n, and each x in the numerator is replaced by quantity u minus b over a, and dx equals du over a. Number 6. Numerical integration, trapezoidal rule. Some functions have no simple antiderivatives. In such cases, if the value of a definite integral is needed, it will have to be approximated. We already know one way to approximate an integral, which is computing an area. An area under a curve approximated by rectangles or by trapezoids. It is apparent that the trapezoids give a substantially better approximation on each subinterval. Basically, the form says that you can approximate an integral from a to b. Assume we chop it up into sections. We take delta x over 2, which is the length of the interval divided by the number of sections. Then we just take the function evaluated at the first point plus 2 times the function evaluated at the next one. Take note that there are 2's all inside, not until the very last section. Then we have x sub I given the formula a plus I delta x.
Let's discuss the integration involving exponential functions. There are two basic formulas. The first one, with base e, is the integral of e to the x dx equal to e raised to x plus c. We've learned about the increment method in our lessons in derivatives. By the formula f prime of x equal to the limit f of x plus delta x minus f of x all over delta x as the change in x approaches 0, we will find the derivative of e raised to x, which is also e raised to x. And because of this, we can say that the integral of e raised to x dx is equal to e raised to x. This is the formula of the base e, or Euler's number. The second example of integration involving exponential functions is the integral with base a, where a is a constant. The integral of a raised to x dx is equal to a raised to x all over ln e plus c. Now let's move on to the integration involving logarithmic functions. The function of the natural logarithm of x is y equal to ln of x. By exponentiating this function, we will get e raised to ln of x is equal to x, and is one of the properties of the natural logarithm and Euler's number of exponential functions. Since e raised to y is equal to e raised to ln of x, then e raised to y is equal to x. If we get the derivative of both sides of this function, we will obtain 1 over e raised to y. But since y is equal to ln of x, and e raised to ln of x is equal to x, then we will be left with 1 over x. We will have the derivative of the natural logarithm of x by getting the antiderivative of 1 over x. Therefore, we will obtain the integral of 1 over x dx equal to ln the absolute value of x plus c. Exponential and logarithmic functions have various applications, especially in economics, where these equations are applied in interest rate calculations on savings, investments, and loans. And biology, where animal and plant population growth and death rates are calculated and predicted using exponential functions. For the integration involving trigonometric functions and integrals, we need to know about the 8 trigonometric identities, which can be found using a unit circle. We can form a right triangle by placing a point on the unit circle. We're already familiar with the coordinates of each of these lines, if we recall the Pythagorean theorem. The hypotenuse will be equal to 1, the adjacent will be equal to x, and the opposite will be equal to y. Because of the unit circle, we get formulas like sine of theta is y, cosine of theta is x, and tangent of theta is y over x. You might be wondering why these formulas seem familiar to you. as you can see, this reminds us the 6 trigonometric functions. Now, let's create new definitions for all of these functions. But instead of thinking of them as coordinates of a unit circle, we're going to consider them only as terms of the trigonometric functions. For example, if the sine of theta is equal to y, then y is equal to the sine of theta. And if the cosine of theta is equal to x, then x is equal to the cosine of theta. Or, if tangent is equal to y over x, then we can rewrite tangent as the sine of theta over the cosine of theta. We will use the same process to identify the other trigonometric functions. After evaluating all this, we'll think about what else we can create from a right triangle. This is where the formula of the Pythagorean theorem comes in. And from what we've discussed, we can now rewrite this as cosine squared of theta plus sine squared of theta equals 1. This now becomes the first of 8 trigonometric identities. And if we have 2 equations where we transpose sine in the first and cosine in the second, we'll get 3 of 8 identities. To get the 5 other trigonometric identities, we'll just use the same substitution process earlier when we created a new definition for these functions.
Here we have the theorems that we'll need for integrating trigonometric functions. Let's solve a problem by using one of these formulas. For our example, we have to get the integral of 3 sine x plus secant squared x dx. First, let's separate 3 sine x and secant squared x by applying the sum and difference rule of integration. We already have an answer for the integral of secant squared x dx, so we'll focus on removing the constant, which is 3, from the integral of 3 sine x dx by applying the constant multiple rule for integration. The equation will now become 3 integral of sine of x dx plus integral of secant squared x dx. Now, we can apply the formulas for the integral of trigonometric functions, and let's not forget the arbitrary constant. For the last step, since we still have 3, we can simplify this by multiplying it to the negative cosine of x. Our final answer is negative 3 cosine of x plus tangent of x plus c.
Have you ever wondered how we will be able to measure the area under any curve? In this section, I will discuss the area and the Riemann sum. In mathematics, a Riemann sum is an approximation of region's area obtained by adding up the areas of multiple simplified slices of the region. It is named after 19th century German mathematician Bernhard Riemann. How is Riemann sum related to area? The limit of Riemann sums gives the net area of the region between the graph and an interval on the axis. So there are 3 basic types of Riemann sum. The first one is the left endpoint sum. The second one is the right endpoint sum. And the third is the midpoint rule. No matter what, every method begins the same way. The first step is to find the delta x. Next step is to find the points x sub I. To understand better, let's have an example. Suppose that we have a graph. So, how can we calculate the area under a curve from, let's say, 0 to 8? How can we determine the shaded area? Now, one way we can do is with the use of rectangles. So let's use rectangles to measure the approximate area and specifically 4 rectangles. So n is represented as rectangles. And we're going to break it into 4. So we will have n is equal to 4. Since the left Riemann sum type is what we are using, the first rectangle from left endpoint is gonna be a 0. And when x is 2, it is gonna touch the curve and so on. So as you can see, it is just an under approximation and it is less than the actual area of a curve. To calculate the area of a curve, we will be multiplying the width times the height. And we need to do that in every rectangle. So we will come to the process and formula of the area is equal to the sigma times delta x times f of x of I. Remember that delta x is represented as the width while the height is the f of x. Next, to determine what is the value of delta x, we will have a formula of delta x is equal to b minus a over n, in which a represents the first point and b represents the end point while n represents the rectangles. So we want to calculate the area from 0 to 8, and that is from a to b. So delta x is going to be 8 minus 2 over 4. That will give us the answer of 2. Therefore, the delta x is 2. If we wish to calculate the area of each rectangle using the formula of height, y is equal to x squared. Therefore, when x is 0, so the height is 0. And when the x is 2, the height is gonna be 4. And when the x is 6, the height is going to be 36. Now, we will calculate the area of each rectangle, that is width times the height. So, 2 times 4, that will give us 8. Next, 2 times 16, that will give us 36. Next, 2 times 36, that will give us the area of 72. So, to get the total area, you will add the all area in each rectangle. So, we will have 8 plus 32 plus 72. That will give us the area of 112. So, we will come up with a process that would help us better. So, we will have the area using the left endpoint, that is equal to delta x times f of x of 1 plus f of x of 2 plus f of x of 3 plus f of x of 4. So, from 0 to 8, and since we use the left Riemann sum, and we will use the endpoint, that is 0, 2, 4, and 6. From the formula, we will substitute the given value that will give us the delta x times f of 0 plus f of 2 plus f of 4 plus f of 6. Now, f of 0 is going to be 0, f of 2 is going to be 4, f of 4 is going to be 16, and f of 6 is going to be 36. To sum up, that will give us the answer of 2 times 56, which is equal to 112, and that is the approximate area under the curve. The next type is the right Riemann sum. Here, we're going to draw a function f, and we will have the same interval of a to b. And just like in the left Riemann sum, we will divide it to measure the approximate area of the curve. So, a will be x sub 0, and b will be the last, which is x sub n. And we're going to add up from 0 and whatever gonna be the value of x sub I is. Again, the distance between the x sub 1 and 2 is the width, which is the delta x. And since we use the right Riemann sums, so the point is going to be at the right, and f of x is our height. We will come up to the process of the area using the right Riemann sum is equal to the delta x times f of x sub 1 plus f of x sub 2, and so on from the last number of f of x sub n. So we will have the summation of delta x times f of x sub I. So the last part is the midpoint Riemann sum. And as you can see, the point is at the middle. And we will have the x bar from the midpoint of each rectangles, since x bar represents the average. And we will come up with the formula of this. Then, the area using the midpoint Riemann sum is equal to delta x times f of x sub 1 bar, and so on. Now, we will get the formula of the summation of delta x times f of x sub n bar. And this is how we use the Riemann sum.
There are two methods of computing volume of a solid figure, the disk method and the washer method. The disk method allows us to calculate the volume of solids of revolution using cylindrical disks. It is called disk method because if we imagine a function and revolve it along the x or y axis, we will be able to produce a cone, and if we slice a piece from it, we will be able able to produce a disk. The formulas of this method are these two. We will use v is equal to pi times the integral of f of x squared dx from a to b if it is horizontal axis of revolution. On the other hand, we will use v is equal to pi times the integral of f of y squared dy from a to b if it is vertical axis of revolution. So here is an example of solving a volume of a solid figure using the disk method. Calculate the volume of the solid produced when the region bounded by y equals x squared, our x-axis, and the lines x equals 0 and x equals 4 revolve around the x-axis. Our formula will be v is equal to pi times the integral of f of x squared dx from a to b, since it is horizontal axis of revolution. Now let's identify and substitute the elements given in the problem. Our f of x is x squared, a will be 0 and b is 4. Then substitute it in the formula. V is equal to the pi times the integral of quantity x squared dx from 0 to 4. Just simplify. Now we got v equal to pi times the integral of x to the 4th power dx from 0 to 4. And then by applying the power rule of integration, we will be able to get v equal to pi x to the 5th all over 5 from 0 to 4. Now, by evaluating it from 0 to 4 and by further simplifying, we will be able to get the final answer, which is v equal to 1024 pi all over 5 unit cube. Similarly to the disk method, washer method is also used to solve the volume of a solid figure. But the only difference is that it has a hole in the center of the cylindrical cone, and when you slice a part of it will look like a washer. These two are the formulas of washer method. V is equal to pi times the integral of quantity f of x squared minus quantity g of x squared dx from a to b if it is horizontal axis of revolution. On the other hand, we will use v is equal to pi times the integral of quantity f of y squared minus quantity g of y squared dy from a to b if it is vertical axis of revolution, wherein our f of x and f of y is the outer radius and g of x and g of y is the inner radius. Now, let's try to solve a volume of a solid figure using the washer method. Calculate the volume of the solid produced when the region bounded by y equal to x and y equal to x squared, our x-axis, and the lines x equal to 0 and x equal to 1 revolve around the x-axis. So the formula again that we will use is v is equal to pi times the integral of quantity f of x squared minus quantity g of x squared dx from a to b, since it is horizontal axis of revolution. Now, to start things off, let's identify first the given elements in the problem. So, f of x is the x, g of x is the x squared, a will be 0 and b is 1. Then substitute it in the formula. V is equal to pi times the integral of quantity x squared minus quantity x squared dx from 0 to 1. So, with the help of power rule of integration and by evaluating the equation from 0 to 1, we will get v equal to pi times the quantity of 1/3 minus 1/5 minus 0. And then by simplifying one last time, we will come up with v equal to 2 pi over 15 unit cube. And that's it. That's our final answer.
Calculus, 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 calculus. The calculus course is a giant course. It may feel and listen that is sometimes true. Now the calculus course may drive you crazy. It may feel trapped in a cycle if you're trigonometry. It's the derivative. It's the derivative. It's the integral. It's the integral. It's the sigma to infinity. There are so many uses of the derivative. You can find them in a mix of velocity. If a function's differentiable a to b, you can find the average rate with the MVT. It's the derivative. It's the derivative. It's the integral. It's the integral. It's the sigma to infinity. Calculus.